So let us now discuss the common forces that we will face while solving the problems. So the first force is the gravitational pull by the Earth. So whenever we have any body of mass m near the Earth's surface, then a force of gravity applied on the body that tries to pull the body toward the center of the Earth. This force is also called as the weight of the body. So it is represented by mg, where m is the mass of the body and g is the acceleration due to gravity. And this is represented by Wm. So you have to just remember that whenever you have a body near the Earth's surface, a weight or a force due to the Earth's gravitation applies on it, and it is given by m into g, where g is the acceleration due to gravity. The other force is tension. So whenever you have a block of mass m or any body that is attached to a string, then a tension force applies on the in the string. So this force is this force applies in the opposite direction of the in which the block is hung, that is away from the block. So it's represented by T. So this covers our gravitation and tension. So let us now discuss spring force. So whenever we have a block that is attached to a spring, and let's say the natural length of the spring is L0, the natural length means the unextended length. That is when the spring is not stretched or compressed. So this is our natural length. And if we just stretch the spring to a distance x from its natural length, a restoring force will act on the block that will try to push the spring towards its natural length, and this restoring force is given by F is equal to minus kx, where k is the spring constant and it depends on the property of the material of the spring. So we have covered gravitation, tension, and the spring force. And the fourth force is normal reaction. So whenever we have a block on the surface, then a contact force between the surface of the block and the surface on which it is resting applies on the body, and this force is known as normal reaction. It's a contact force that arises when two bodies are in contact. So this is represented by N or R. So up until now we have covered gravitation, tension, spring, and normal reaction. Now we will discuss friction. So let us now discuss inertial frame and the non-inertial frame of reference. So an inertial frame of reference is a frame of reference that moves with a zero acceleration. That is, it doesn't accelerate. So if we have a inertial frame of reference, that means it can either be at rest or can move with a uniform velocity. So if a frame is at rest or is moving with a uniform velocity, it means it is unaccelerated. An unaccelerated frame of reference means its acceleration is equal to zero. So Newton laws are only valid in inertial frame of reference. So Newton laws are valid only in inertial frame of reference. Frame of reference. So we don't know how to apply Newton laws in non-inertial frame of reference. So we will now see how to apply Newton laws in accelerating frame. So how to apply Newton's law in non-inertial frame. Non-inertial frame, that is accelerating frame. A is not equal to 0. So suppose I have a elevator, and in the elevator I have a block of mass m, and if this block is moving upward with an acceleration a0, then we don't know how to apply Newton's laws in this frame of reference. that is in the frame of elevator, because now we have a accelerating frame of reference and we don't know how to apply Newton's laws in accelerating frame. So suppose that I have two frames I, that is inertial, and another frame Ni, that is non-inertial, and I have a point particle P of mass mp. The position vector of P with respect to non-inertial frame of reference is rp ni, and if this ni is moving with an acceleration of ai ani I dash ani with respect to I, which is equal to a naught, that means the acceleration of the non-inertial frame of reference with respect to I is a naught, and the position vector of P with respect to inertial frame is API, sorry, RPI. So if I take double time derivative of this position vector, I will get acceleration in the inertial and the non-inertial frame of reference. So API is equal to R double dot PI, and similarly APNI is R double dot PNI. The double time derivative of the position vector give us the acceleration in the respective frames. So if I now apply the triangle law of addition, I'll get A naught plus APNI is equal to APNI. So if I now apply by mass on the both side, that is mass of point particle P on both side, I will get APNI is equal to MP AP with respect to I minus MPA naught. So we have the force in the frame of reference that is moving is equal to force in the inertial frame minus the acceleration of the non-inertial frame. So this part is known as the pseudo force that applies on a body when it is in accelerating frame of reference. For example, let us consider the same example of mass m in an elevator. When we are in elevator, if the elevator is accelerating upward with an acceleration of a naught, then a force of m a naught applies on it in the downward direction. So this force is our pseudo force, that is the force that we experience in a accelerating frame of reference. So the net force that we will feel will be mg plus a naught. So that is why when you are in an elevator and when it moves upward, you feel a little bit heavy. That is, you push you are pulled more towards the ground because of this pseudo force that applies when the frame, that is our elevator, is accelerating upward. So let us now solve more problems on. Let's now solve this first problem. We are given that we have two masses of 1 kg and 2 kg that are hanging from a string by a pulley, and we have to calculate how much time it takes for the two blocks to cross each other. So for example, if I just keep the system to fall under the force of gravity, if the system just move under the force of gravity, we have to calculate the time at an instant when the two blocks that of mass 1 kg and 2 kg cross each other. So let us first draw the force body diagram for the two bodies. So let us say I have a body of 1 kg, and the forces that are acting on this body is tension from the string and mg, that is the mass. So we can write the weight as 1g. And similarly for mass of 2 kg, we can write tension from the string to be T because the string is the same, so the tension will also be T. So and the weight will be 2g. So if I consider the 2 kg block to be moving downward, I can write T 2g minus T is equal to 2ma, and for 1 kg block which will move in the upward direction if the 2 kg block is moving downward, I can write T minus G is equal to ma, where this m is equal to 1. So this will be equal to 12 2a, and this will be equal to a. And the acceleration is equal in both the cases because we have a constraint on the system. If I just call this L1 and I call this L2, I have L1 plus L2 is equal to constant, which is the length of a string. So I can take time derivative, double time derivative, and I will get L1 double dot is equal to L2 double dot. And the negative sign shows that the motion of the two blocks are in the opposite direction. That is, if the 2 kg block is moving downward, then the 1 kg block is moving upward. So if I solve these two equations for t, I'll get g is equal to 3a and a is equal to g by 3. So let us say initially the 2 kg block is at a distance of 10 meters from the block of 1 kg, and let's say at a time t the block of 1 kg move upward with a direction of upward with a distance of x, and the 2 kg block move downward, that is when they meet each other. So this distance from the initial point will be 10 minus x. So if I just apply the kinematics law, I can write for the 1 kg block that x is equal to half g by 3 t square. And similarly for the 2 kg block, I can write 10 minus x is equal to half g by 3 t square. And the t is same because they meet at the same, they process each other at an instant t, which is same for both of these blocks. So I can substitute the value of x over here. I can, and in the end I will get half g by 3 t square is equal to half g by 3 t square. And if I take this term to the right, I'll get g by 3 t square. So 10 can cancel each other and I'll get t is equal to root 3 second. So the block will cross each other at time t is equal to root 3 second. So this completes our question number 1, and we have just seen that how can we apply Newton's laws of motion and kinematics to solve the pulley mass problem. And we have to just draw the FBD and just keep in mind what are the constraints, and have to formulate the equation and solve for the acceleration, and then just apply kinematics. So let us now try to solve this very elementary question on the Newton's laws of motion. So suppose that I have a bullet of mass 0.04 kg moving with a speed of 90 meter per second, and it enters a heavy wooden block and it's stopped at a distance of 60 centimeter. We have to calculate what is the resistive force exerted by the block on the bullet. Okay, so we have to calculate the resistive force, and we are given that the Mass of the bullet is 0.04 kg and the speed of the bullet is 90 meter per second. And when it enters the block, it stopped at a distance of 60 centimeters. So if I have this block and a bullet is striking this block, so after traveling 60 centimeters within the block, the bullet stops. So we have to calculate what is the resistive force that was offered by the block which compelled the bullet to come to a state of rest. So we are given mass of the bullet is 0.04 kg and the initial speed of the bullet is 90 meter per second and the distance traveled by the bullet is 60 centimeters. When we will change it to meters, it will be 60 upon 100. So it will be 0.6 meter. And we have to calculate acceleration because force is directly proportional to acceleration by a relationship F is equal to ma, where m will be the mass of the bullet. So by applying laws of kinematic rule, v square minus u square is equal to 2as, we can calculate the acceleration of the block within the acceleration of the bullet within the block because before entering the block, the bullet was traveling at a constant speed of 90 meters per second, but in the block, a resistive force acts on this bullet and will compel it to come to rest. So we have to apply v square minus u square is equal to 2as, where final velocity will be equal to 0, initial velocity will be equal to 90 square, and 2 will be 2, and acceleration we have to find out, and s will be equal to 0.6. So a will be equal to minus 90 squared upon 2 into 0.6, and I got a negative sign which basically tell us that the force or the acceleration is negative, that is it's a retarded motion. The acceleration is the velocity is decreasing with the time. It basically tells that. And if I now apply F is equal to ma, I can calculate the resistive force that is offered by the block on the bullet which compelled it to come to rest. So F is equal to 0.04 into 90 square upon 2, 0.6. So this will be the resistive force that was offered by the block to the bullet and which compelled the bullet to come to rest. So we have seen basically how to solve a problem of Newton's laws of motion using the kinematics formula and remembering a simple relationship between force and acceleration. So the relation is F is equal to mass is into acceleration. So this will be the answer of this. So let us now solve this problem. We are given that we have a particle of mass m that is thrown upward with a velocity of v, and other than experiencing the gravitational attraction from the earth, it also experiences a drag force which is proportional to the square of the velocity. And if the particle attains a maximum height after time t, and we have to calculate what is the velocity v, which is dependent on time. So you have to calculate velocity at a time t at which the particle attain a maximum height. So let us now first draw the force body diagram for this question. So if the ball is thrown upward, the gravitational attraction due to the earth will be downward, and the retarding force that will retard the motion of the body will also apply in the downward direction because the ball is moving upward. So which is equal to minus kv square. This is the retarding force and this is the weight of the body. So I can write the equation for it, which is equal to minus kv square minus mg. This is the equation that we have to solve, and we have to evaluate what is the velocity of the body. So to get a relation between the velocity and time, I have to eliminate x because we don't require the information of x from the equation. So to eliminate x from the equation, what I can do is m dv by dt, which is the acceleration of the body, which is equal to minus kv square minus mg. Because dx by dt is the velocity, so I can write d square x by dt square is equal to dv by dt, because acceleration is also the time derivative of the velocity. This is the other definition for the acceleration, so I can write this. And if take mass to this side, I can write dv by dt is equal to minus kv squared by m minus mg by m. So I can cancel the mass and I'll get dv by dt is equal to minus kv squared by m minus g. So this is the equation that we have to solve. So this is a differential equation, and to solve it we must know how to do integration. So I can rearrange the terms and can write the equation as dv upon kv square by m plus g is equal to minus dt. So I have to integrate this equation, and I can also apply the limit, and the limit of this integration will go from 0 at t equal to 0. The velocity will be v, and at the highest point, that is when the ball attain the maximum height, at that point the velocity will be equal to 0. And over the right side I'll have the integration from 0 to t. So I can integrate the right hand side and can write minus, I can write I can integrate dt and can write t over here. But what I can do is take the negative sign to the left and change the limit to 0 to v. dv by kv square by m plus g is equal to dt from 0 to t. I can take this minus sign over here and can rearrange the limit. So this is the integration that we have to solve now. So let us now solve this integration. So to solve this integration, we have to remember the formula of this integration, because this will use the tan integration. So this will be dv upon k by m v square plus g from 0 to v is equal to t. This is the integration, and what I can do is I can take k by m common from the denominator and can write 0 to v dv upon k by m is common, so v square plus g m by k. Okay, so and over there we have t. So the question asks, what is the velocity at the, what is the initial velocity that we throw the object with, and this will be time dependent. So because at the height, after a time t the ball attain a maximum height, at that point the velocity will be 0, and at the initially the velocity will be some v from where it will be launched, with that velocity it will be launched. So let us now solve take a step further and solve this integration. So I can rearrange the denominator and can write m by k 0 to v dv upon v square plus gm by k is equal to t. And to solve this integration, what, what more I can do is in the denominator m by k 0 to v, I can write the second term as under root of gm by k whole square, which is equal to t. And from the integration formula, you know that 1 upon x square plus a square integration dx is equal to 1 by a tan inverse x by a. This is the integration formula for this that will be required to solve this problem. So let us now use this integration formula. So it will be m by k into 1 upon root gm upon root k tan inverse v root gm root k is equal to t. Then I can simplify this term. I'll get m by k root upon 1 by root g tan inverse v root k upon root gm is equal to t. And if I take this whole term to the right, I'll get tan inverse v root k upon root gm is equal to root kg by root m t. So taking tan to the side, I'll get v root k root gm is equal to tan root kg upon root m t. So I can take this whole term to the right and rearrange the expression and get the value of v from v, that was the initial velocity by which the particle was thrown upward. So this will be our value for the velocity at which the particle was launched, and at the highest point the velocity will be 0, and initially it was thrown by a velocity v, and in an interval of time t the particle attain a maximum height. So at this point v will be equal to 0. So, and by using calculus and integration and force body diagram, that is by using Newton's second law, that we drawn like this, we formed a differential equation, a first order differential equation in v, and then evaluated the velocity, that is the initial velocity by which the particle was thrown upward. So we see how we can use mathematics and integration and calculus and Newton's law to calculate the value or the quantities that we are interested to evaluate. We'll do more problems on this of this type